This video will focus on the concept of momentum. We will cover the relationship. Momentum equals mass times velocity. P equals m times versus. We will also look at safety features, the conservation of momentum, and Newton's third law. Finally, we will examine the relationship. Force equals change in momentum divided by time taken. Momentum, or P, is calculated as mass times velocity, or P equals m times, versus mass is measured in kilograms, velocity in meters per second, meter per second, and momentum in kilogram meters per second, kilogram meter per second. Momentum has both magnitude and direction, which is the same as the velocity. The greater the mass or velocity of an object, the greater its momentum. Let's calculate the momentum of a rugby player with a mass of 120 kilograms moving at 3 meters per second. Using P equals m times v, we get 120 kilograms times 3 meters per second, resulting in a momentum of 360 kilograms meter per second. Next, let's calculate the mass of a car moving at 25 meters per second with a momentum of 20,000 kilograms meter per second. Starting with P equals m times v, we rearrange it to find mass. M equals P divided by versus. So 20,000 kilograms meter per second divided by 25 meters per second gives a mass of 800 kilograms. Pause the video and complete the table by calculating the missing values for momentum, mass, or velocity. Here are the answers to the table for you to check your work. A force will cause an object's velocity, and therefore its momentum, to change. A greater force results in a faster change in momentum. Considering acceleration as the velocity change divided by the time taken, and applying Newton's second law, F equals ma, we can derive that force is the change in momentum divided by the time taken. The relationship can be written as force equals momentum change divided by the time taken for the change. Force is measured in newtons, N, change in momentum in kilogram meter per second, and time in seconds, S. Let's calculate the force required to change a car's momentum by 24,000 kilogram meter per second over a 6-second period. Force equals momentum change divided by time taken. 24,000 kilograms meter per second divided by 6 seconds equals a force of 4,000 newtons. Next, let's calculate the time taken for a force of 6,000 newtons to change the momentum of a truck by 42,000 kilogram meter per second. Rearranging the formula, time taken equals momentum change divided by force. So 42,000 kilograms meter per second divided by 6,000 newtons results in a time taken of 7 seconds. Momentum is conserved in any collision or explosion, provided no external forces act on the colliding or exploding bodies. This means the initial momentum of the yellow car is transferred to the red car. Let's consider an example. A 0.5 kilograms truck moving at 1.2 meters per second collides and remains attached to a stationary 1.5 kilograms truck. Calculate their common velocity after the collision. First, calculate the total momentum before the collision. 0.5 kilograms times 1.2 meters per second plus 1.5 kilograms times 0 meters per second equals 0.6 kilograms meter per second. Since momentum is conserved, the total momentum after the collision is also 0.6 kilograms meter per second. The common velocity is 0.3 meters per second. Question 2. A train wagon of mass 800 kilograms moving at 4 meters per second collides with a 1,200 kilogram wagon moving in the same direction at 2 meters per second. They remain attached. Calculate their common velocity. The total momentum before the collision is 800 kilograms times 4 meters per second plus 1,200 kilograms times 2 meters per second, totaling 5,600 kilograms meter per second. As momentum is conserved, this is also the momentum after. The common velocity is calculated as 5,600 kilograms meter per second divided by the total mass of 2,000 kilograms, which equals 2.8 meters per second. In head-on collisions, bodies move in opposite directions. Since momentum has direction, one direction is treated as positive and the opposite as negative in calculations. A 1,000 kilograms car at 20 meters per second makes a head-on collision with a 2,000 kilogram lorry at 16 meters per second. They remain attached. We need to calculate their common velocity after the collision. If the car's velocity is positive 20 meters per second, the lorry's is negative 16 meters per second. The total initial momentum is 20,000 kilograms meter per second plus negative 32,000 kilograms meter per second, resulting in negative 12,000 kilograms meter per second. The common velocity is negative 4 meters per second. The combination moves in the original direction of the lorry. Question 2. A 1,000 kilograms car at 30 meters per second collides head-on with a 2,000 kilogram lorry at 15 meters per second. They remain attached. Calculate their common velocity. The car's momentum is positive 30,000 kilograms meter per second. The lorry's momentum is negative 30,000 kilograms meter per second. The total initial momentum is 0 kilogram meter per second. Since momentum is conserved, the combined vehicle will not move after the collision. For explosions, the total momentum before the explosion is 0. Because momentum is conserved, the total momentum afterward must also be 0, meaning the parts must move in different directions. An artillery gun of mass 1,500 kilogram fires a 20 kilogram shell at 150 meters per second. Calculate the recoil velocity of the gun. The total momentum before and after the explosion is 0. The shell's momentum is positive 3,000 kilograms meter per second. Therefore, the gun's momentum must be negative 3,000 kilograms meter per second. This results in a recoil velocity of negative 2 meters per second, meaning the gun moves backward at 2 meters per second. A girl of mass 60 kilograms throws a boy of mass 90 kilograms out of a swimming pool at 2 meters per second. What is the girl's recoil velocity? The total momentum is 0. The boy's momentum is positive 180 kilograms meter per second. The girl's momentum must be negative 180 kilograms meter per second. This yields a recoil velocity of negative 3 meters per second. The girl moves to the left at 3 meters per second. Safety features like crumple zones and airbags are designed to increase the time taken for a passenger's momentum to change to 0 during a crash. Increasing the time taken for the same momentum change decreases the force exerted, reducing the risk of injury. This is based on the equation: force equals momentum change divided by time taken. Consider playground rubber tiles. They increase the time taken for a child's momentum to change from a high value to 0 when falling. By increasing the time taken, the force on the child is reduced, lessening the potential for injury. Newton's third law states that forces always occur in equal and opposite pairs. This is often summarized as, to every action there is an equal and opposite reaction. In a rocket launch, the thrust of the engines exerts a downward force on the ejected gases. Conversely, the gases exert an equal and opposite contact push upwards on the rocket engines, propelling the rocket. A car moves forward because of the friction force of the road on the tire. This force is equal and opposite to the friction force of the tire on the road. Pause the video and choose the appropriate words to fill in the blanks in these sentences about forces in motion. Here are the answers. A force is a push or a pull. A force can cause an object to accelerate or change shape. Force is measured in newtons with a Newton meter. Contact force occurs when two bodies touch. Forces always occur in pairs. If a force is exerted on an object, there will always be another force, equal in size, acting in the opposite direction.